there! I am Dr. Dacia Milescu, Adjunct Professor at Daytona State College, and today's little mini lesson will be understanding muscle contraction via what we call the cross-bridge theory. This is the best theory that we have analyzing all the way down to the molecular level muscle contraction. So there are major steps leading to muscle contraction. So we are going to embark on the journey of understanding the phases leading to muscle contraction. So let's begin. Okay, the three phases leading to muscle contraction are Phase 1, events at the neuromuscular junction. There are several steps there we will discuss. Phase 2, excitation, contraction, coupling. And Phase 3, cross-bridge cycle. Let's discuss Phase 1, events at the neuromuscular junction. First step, the action potential travels down the axon and reaches the axon terminal. Voltage-gated calcium channels will open at this point and calcium is released. This calcium ion release causes the synaptic vesicles to further release the acetylcholine. Acetylcholine travels across the synaptic vesicle and reaches the acetylcholine receptor on the motor end plate. The acetylcholine binds to the acetylcholine receptor, causing the channel to open. Sodium diffuses in, while potassium diffuses out at a 3:2 ratio, causing the membrane to depolarize and become less negative. Action potential continues down the sarcolemma. So that is Phase 1. Let's take a look visually at what these steps are. So we see here a muscle fiber, which basically translates into a cell, the cell of a muscle. And one muscle fiber has what's called a membrane called the sarcolemma. So here is a motor neuron with the axon. It interacts with the muscle fiber. This space here is called the neuromuscular junction. So the phases are three, right? Events at the neuromuscular junction, excitation, contraction, coupling, and cross-bridge cycle. So in this image, all we are looking at is the first phase, events at the neuromuscular junction. The arrow here indicates the action potential traveling down the axon and reaching the axon terminal. That was step 1 in events at the neuromuscular junction. Step 2, the voltage-gated calcium channels open, and this arrow indicates the calcium rushing in to the axon terminal. That was step 2. Step 3 was the synaptic vesicles at the axon terminal release the neurotransmitter called acetylcholine. So here it is being released via exocytosis, which is a form of active transport. All right, the next step is that this acetylcholine, the neurotransmitter, travels across the synaptic cleft, this is the cleft right here, and reaches the postsynaptic side, which basically is the muscle fiber. Well, in this area here, we call this area that's infolded the sarcolemma, the membrane that's folded up here, we call that the motor end plate. So at the motor end plate on the muscle fiber, we have these acetylcholine receptors, totally waiting, receptive, and responding to a molecular bonding with the neurotransmitter acetylcholine. All right, so the next step is the acetylcholine binds to the acetylcholine receptor, and the acetylcholine receptor channel opens. When this happens, that's the final step here. You can see sodium rushing in, diffusing in, and potassium diffusing out at a 3:2 ratio, causing this entire motor end plate to become less negative. We call that depolarization. This continues down the line to Phase 2, which is our next slide. Phase 2. Phase 2 involves excitation, contraction, coupling. The action potential travels down the T-tubule and reaches the voltage-gated proteins around the sarcoplasmic reticulum, SR. Now, the sarcoplasmic reticulum triad consists of two terminal cisternae. Those are the bulging sac-like structures that are part of the sarcoplasmic reticulum, interfacing with one T-tubule. That's where we have voltage-gated proteins. They change the shape once the action potential reaches this voltage-gated protein. And so once the voltage-gated protein changes shape, it releases copious amounts of calcium into the SR, known as sarcoplasmic reticulum. So in this phase, there are only two steps, right? Step one was the action potential traveling down the T-tubule and reaching the voltage-gated protein. Step two, the voltage-gated protein changing the shape and releasing the calcium into the sarcoplasmic reticulum. All right, so let's go to the next phase, the third and final phase. But before that, this is just an image to show you exactly what I just described. The excitation-contraction coupling, you can see the next steps after the action potential traveling across the motor end plate. It continues down the sarcolemma and now down the T-tubule, and all the voltage-gated proteins are changing shape, and the two sac-like bulging structures here are part of the sarcoplasmic reticulum. This is where these proteins are located. So these proteins change shape and release massive amounts of calcium here in the sarcoplasmic reticulum. And so now the next steps are going to be the final phase, the cross-bridge cycle, because this calcium is going to bind to the thin filament and initiate the final steps, cross-bridge cycle. So that's what we're looking at here. So let's take a look at the next slide and understand the steps to the cross-bridge cycle. So here we go. Cross-bridge cycle. Calcium binds to troponin and causes the thin filament to change shape, thus exposing the actin molecule to the myosin head located on the thick filament. Next step, the thick filament has the myosin head prepping into the cocked position. 1 ATP is used. The myosin head attaches to the actin, forming the cross bridge. 1 ATP is used. The power stroke occurs, causing the myosin head to pivot on the actin, causing muscle contraction. Another ATP is used. Detachment occurs, whereby the myosin is released from the actin. Another ATP is used. The myosin head returns to the cocked position. 1 ATP is used. Actin goes back to the original position as thin filament returns to the normal shape once calcium is no longer binding to troponin. All right, so I'm going to go back to this image and show you what exactly is happening. So all this calcium, this is the cross-bridge cycle, final steps that I just described. Here is the calcium, and it's going to bind to the troponin on the thin filament. This whole troponin on the thin filament causes the thin filament to change shape and expose the actin molecule, seen here in yellow, to the myosin head seen on the thick filament. Now, once the calcium binds to troponin and changes the shape of the thin filament, in turn, the myosin head moves into the cocked position and an ATP is used to do that. Now, the cross-bridge binding occurs, the cross-bridge formation occurs, whichever terminology you want to use. Once the cross-bridge forms, another ATP is used. What does that mean? It means that the myosin head is now binding to the actin on the thin filament. Then, the power stroke. Here is where the myosin head pivots on the actin molecule and another ATP is used. This is called the power stroke. Okay, and then finally after the power stroke we must have detachment. We cannot continue muscle contraction forever. So therefore the myosin head detaches and another ATP is used for that. Eventually the myosin head goes back into the original cocked position. the calcium is released from the troponin and the thin filament goes back to its original shape. Okay, so that's pretty much it. This is another image to show you the steps in sequence. Step 1. The myosin cross bridge attaches to the actin myofilament. Step 2. ATP, as you can see here, ATP is used. ATP is used here in terms of the power stroke. So with the power stroke, the myosin head pivots and bends as it pulls on the actin filament, sliding it towards the M line, meaning shortening the muscle fiber. Okay, great. ATP is used for that. Now check it out. The myosin head must detach. Another ATP is used for that. Okay, as ATP is split into ADP, the myosin head becomes cocked again. It's into its original cocked position, meaning it goes back up into its original position, ready to fire up again and continue this cross-bridge cycle every single time a calcium binds to the troponin on the thin filament. Okay, I do hope that this tutorial was helpful for you in understanding muscle contraction.